This topic is about learning compatible embeddings. Let's introduce the motivation of our work. Here's the picture that describes the pipeline of phase matching between prop and gallery. If the prop and gallery features are extracted from the same model, it is very easy to get reasonable matching results. However, especially in industrial area, where prop model is upgraded while the gallery model remains their old version, we could get bad matching results. A straightforward solution is backfilling, that is, using new model to extract features of old gallery images, which is not a good solution, firstly because it suffers from the high computational costs. Secondly, backfilling is infeasible if no gallery image is available, which is a common scenario these days, since collecting face images is prohibited in many countries for privacy issues. So, we need a model compatibility solution to bypass these restrictions. It is a brand new academical topic, while has great practical value. We know this application scenario of model compatibility is diverse. In the perspective of training models, it can be categorized into cross-model compatibility and compatible training. Cross-model compatibility requires two models be already, such as pre-trained models, while compatible training trains model 2 only and make it compatible with model 1. Model compatibility can also be divided into direct, backward, forward, and double forward in the perspective of matching directions. Note that double forward is ignored in our work because of the large computational cost. So how to say if two models are compatible or not? Previous works used a pointwise criterion to make two features from the same image be closer. It is a very strict criterion that can degrade new model to the old one. Instead, our method uses a point-to-set criterion to align class centers of the same ID, which loses that restriction so that it relieves the degradation of the new model. Here's the big picture of our method. Model 1 serves as the old model and it is already well trained. Model 2 serves as the new model. Transformation module T1 and T2 are used to decouple the transfer feature from the original one, and it is an indispensable part for cross-model compatibility scenario. For losses, alignment loss aligns class centers from the same ID. We use boundary loss to form a compact inter-class distribution of the new model. Classification loss is also adopted to supervise the training. So let's talk about our experiments. In ablation study, we check impacts of the two losses as well as the transformation module towards our method. It is obvious to see that each component plays a positive role and reaches the summit performance when all components are adopted, which has nearly no performance degradation. We also validate our method in cross-model compatibility scenario. We use 3 pre-trained models in different network architectures, train compatibility modules in different losses, and compare the results of ours and the RBT baseline. The results shows that our method outperforms RBT in both arc phase and norm phase losses. To reiterate our contributions, first, we are the earliest to identify variations of compatibility in applications. Second, we design a unified framework for all compatibility problems. Third, we define new criterion for compatibility and propose our LCE loss. And last, we make extensive experiments to verify our methods. Thank you for your watching and feel free to scan the QR code to grab our LCE code on GitHub.